All right, so welcome to part two. This is my, I've worked on this a couple of times now. Anyway, so we're going to do two more examples here of working with the linear momentum equation. And here we've got, if we zoom in, we've got example two, and here's kind of what it looks like. And this I think of as one of those nozzles that we see in science class. I'm just going to kind of imagine that, it continues to go up into connect into the system. We should note that down at the bottom, it is releasing into the atmosphere, like it's shooting out here. Okay, key. What do you think when you start thinking atmosphere? You start thinking, oh, what do we have to do with the pressure there? Almost nothing. Isn't that beautiful? Right, we have to love it, okay? When you see things squirting out into the air, you should automatically, already, I'm getting like sidetracked from the whole question because I'm so excited. You already know that you want to put a point right here. 2. Okay, why right there? Because the pressure is going to be 0. Okay, and that's what you want. You like that, just going to make your life easier. Okay, we also know something about the cross-sectional area there because we have this 5 millimeter gap. And yeah, so that's really good. Anyway, so this is like one of those little science nozzles. And I think these are about the right dimensions, half a millimeter for the bottom. I mean, half a centimeter for the bottom and 1.6 centimeters for the top. And of course, if you remember these things, whenever I used to turn these things on, the water would just come shooting out like really, really fast. It would it's just really, really fast. Anyway, I'm going to tell you right now where point 1 is going to be. It's going to be right here. Okay, we're going to call this point 1. Okay, and we're going to do that. And in this case, we don't really have a choice because they give us what's given. If I zoom out a little bit, they give us the pressure at 1. Okay, so if they give us pressure at 1, they have to tell us where that pressure is. Okay, and that's where it is. They also tell us something about the mass of water, 3 times 10 to the negative third kilograms. That's the mass that is in this nozzle itself. And of course, it's logical if you were designing one of these things. Okay, so they tell us the mass of the nozzle itself. So the nozzle has a certain weight to it. So that's like all this right here. Okay, so it's made out of some sort of metal. And that metal is circular or conical or whatever shape you want to call it. Conical would be correct, I guess. And it's got a mass of 0.1 kilograms. And the water that's in that is much smaller than that. So maybe this isn't drawn exactly correctly, but whatever. And yeah, and that's all we got. And we know we got 0.6 liters per second. Okay, coming through here. All right, first thing, we don't like some of these units. kPa is pretty easy to deal with, 464,000 pascals or newtons per meter squared. Okay, that we can use. What do we want to do with liters per second? Well, we're going to have to get rid of that, right? So the way we do that, maybe the equal sign is not really the right thing. We need to multiply. Okay, how many liters are in a cubic meter? Well, an awful lot of them. Okay, it turns out that there are 10 to the third liters in 1 cubic meter. So if we do that conversion, we end up with, well, we could just say we don't really have that extra significant digit, but 6. I just erased you punk. What? Come on. Okay, 6 times 10 to the negative fourths cubic meters per second. Okay, that's our Q. Okay, we don't want to work with liters, right? Okay, so now that we have all this in kind of standard units, we get the masses in kilograms, which can be, we can calculate weights by just multiplying times gravity. So that's pretty straightforward. All right, so now what we want to know about the force of anchoring. So basically, if you were designing this system, you would want to know how strong does the connection here need to be. Okay, maybe it's got those little threads, and you want to know how much force those threads need to hold, right? And it's going to depend very heavily on the pressure and how much flow rate you're going to have coming through there. Now, to solve this, what we'd really like is a set of tools, perhaps. Oh, look, we have tools. Oh, we have 2 sets of tools. They're the same set of tools. All right, let's bring these tools down. Okay, we're going to bring these tools down, and we're going to use them. Okay, to figure out what the anchoring force is here. Okay, force anchor to hold this thing on there. Okay, so we're going to look at these things. First of all, let's get rid of some of these tools, right? We're not going to use the manometer here because there is no manometer. There could be a manometer, but there is no manometer. Okay, now notice whenever we want to force on and there's a moving fluid involved, we know we're going to want the momentum equation. And as soon as I know I want the momentum equation, I'm going to draw a free body diagram. And this is going to be of the nozzle and water. Okay, the last time I did this, I did not include the nozzle, and it's because my question didn't ask for the force on the nozzle, right? In this case, the anchoring force is acting on the nozzle, right? So I want that to be a part of my answer. Okay, so basically if I draw the nozzle, and nozzles are hard to draw, okay, I'm going to draw it kind of like I did on the right here. Okay, and it's the nozzle and the water. So here's the nozzle, and naturally, it wraps around, right? So it's actually kind of, whatever. Okay, ugly drawing. But, and then there's the water that's within it, okay? And so maybe I'll draw the water in some kind of color like this, okay? So now we need to think about, well, first thing I like to think about, because I'm going to go momentum equation, is what are the momentum fluxes, okay? So there's momentum coming in here. We'll call that V1. And there's momentum leaving our free body diagram right here, and that's V2, okay? Now we need to think about the forces. Okay, and last time I did the forces in red, so I'll do the forces in red again. Sometimes it can be kind of nice if, if some of you guys are working on either with a multicolored pen or pencil, or if you're working on a tablet like I am right now, and you can say, okay, well, there's a pressure right here. Okay, and technically that pressure is covering a circular area. I'm going to save you my attempt at trying to draw that, so we'll do P1A1. And is there a pressure up on the bottom? P2A2. Well, there should be, but we know that it's atmospheric, so there is no pressure right there, which is awfully nice, okay? Now, what other forces do we have? So we've got, well, let's see. So normally there's a, what we call a body force. So in this case, I'll draw this right here. That's the weight of the water, right? Okay. There's also the weight of the nozzle, which I'm going to draw right next to it. I mean, they act at the centroid, but or the center of mass. I'm going to call that F nos, okay? I don't really know what else to call it. Let's zoom in so we can actually see what I'm drawing here. Okay, F nos. And then what else do we have? Okay, well, based on all of that so far, this nozzle is going to go flying downwards. The only reason it doesn't fly downwards is because there is a anchoring force, okay? It's probably due to the threads of the the nozzle onto the rest of it, or maybe it's welded on there. I don't know how these things work. I'm a fluids guy. So we're going to call that force anchor. Okay, and I think sometimes you'll see that as 4F capital A or something along those lines. Okay, and so now we need to solve for each of these as much as we can using our tools, which are right here, so that we can plug them into this momentum equation. Okay? We can use Bernoulli if we need to. We can use the geometry. We can use continuity. We can use whatever it is we needed to use. Okay? So let's start by looking at those and figuring out which ones we don't know. Okay, do we know P1? Yeah, it's given, right? Boom. Okay, A1, well, we know the diameter of that thing is 1.6 millimeters, so we're not really going to worry about that too much. Okay, so we know A1 or we can get that super easy. Okay, what about, let's see, P1A1, P2A2, there is none. The two weights are pretty easy. Why did I call that F nos? That was silly. Let's not call that F nos. Let's call that the weight of the nos, W nos. All right, let's not be ridiculous here. I mean, let's be ridiculous, but not in that way. Okay. So we can get the weights by doing mass times gravity. This one's actually pretty easy. Let's just go for momentum here. Oh, no. We need these velocities, don't we? You all are going to let me go without doing the velocities, right? I need V1 and V2. Okay, so how do I get V1? Well, I say Q. So basically, I'm going to use a little continuity here and say Q equals V1 A1. Okay, so Q equals, well, V1 is, well, that's what we're looking for. I forgot to put in the Q. So Q is 6 times 10 to the negative fourths. 6 times 10 to the negative fourths cubic meters per second, or CMS. And V1 and A1 is pi times 1.6 millimeters. Okay, so 0.016 meters squared. Woo-wee, that's a small area. So what do we expect? We expect it's probably moving pretty quick, although then again, it's a small flow rate. So what do we get? We end up with If we solve for V1, so we divide, we end up with 2.98 meters per second. That's pretty fast. Okay, just for reference, your typical mountain creek is about 1 meter per second. Okay, now note, what do we expect V2 to be? A lot larger. Okay, so basically, if we divide 16 by 5, we get about 3. If we square that, this should be about 9 times as big. So if I do 3 roughly, 3 times 9, that should get 27 or so. Okay, unfortunately, but of course, this is a little bit larger than 3 times ratio. So this ends up being 30.6. I'll let you do that, that algebra on your own. Okay, boom, boom. Okay. All right, so cool. So now we've got our 2 velocities. So let's go ahead and see if we can't solve this sucker, right? Because it seems like we have everything we need. Okay, so here's our free body diagram, and now we're going to do the momentum equation. So we're going to sum the forces in the z direction plus the sum of the ends of, right, we don't even need to do the x direction, right? It's symmetric in all directions, so we won't even bother with that. So we'll say Vz rho Q equals the sum of the outs of Vz rho Q. Okay, now quick question before we even begin this. What do you think is going to be more important in this case? The momentum fluxes, okay, so these terms, or really I guess the difference in the momentum fluxes, or the pressure and weights, I guess. Right? Usually we're comparing pressures to momentum fluxes when we do this. Which one's going to matter the most? Obviously, the weights seem like they're going to be pretty small, right? These are not very large things. But what about that pressure? That pressure was huge, right? 464 kPa. Well, let's go ahead and find out, right? Okay, so the first thing we have is we have negative P1A1. That's a downward force. Okay, we've got F anchor. Okay, I'm doing all the things in red right now. Minus the weight of the nozzle. Minus the weight of the water. Okay, so those are all of our forces because we got all the red things. There were 4 arrows. Okay, now we got the end. We need an in arrow. We've got a V1. So say plus. Now remember that's got to be a negative. Negative V1. Okay, rho Q equals. Okay, Vz for out is going to be a V2, a negative V2. Okay, rho Q. Okay, and there's no sines or cosines here because everything is straight up and down. And that's how we solve this sucker. We just got to plug some numbers in. Okay, so I don't think there's really a lot of trick here with these numbers. So, but let's go ahead and do it. Okay, so P1 will be minus 464,000 pascals, or newtons per meter squared. Sometimes it can be easier to see that things are working that way. The area is pi times 0.016 meters squared divided by 4. Okay, plus F anchor. Okay, minus the weight of the nozzle, which is, what is the weight of the nozzle? Oh, 0.1 kilograms. 0.1 kilograms times 9.81 meters per second squared. Okay, that's a weight. A lot of you guys make the mistake of plugging this in. Remember, kilogram is a mass. It is not a weight. Okay, minus the weight of the water, which is very small, 3 times 10 to the negative 3 kilograms times 9.81 meters per second squared. Okay, so those are all the weights. And now we're going to do, all the forces, I think. That's all the forces. And then we're going to do the velocity fluxes. Okay, so we're going to have plus negative V1, so negative 2.98 meters per second, times rho. What is rho of water in the SI system? Kilograms per meter cubed. And Q was given as 6 times 10 to the negative 4th meters cubed per second. CMS equals, and here is negative V2, right? Negative 30.6 meters per second. Rho, again, is 1,000 kilograms per meter cubed. And 6 times 10 to the negative fourth cubic meters per second, CMS. All right, so that big, long, nasty equation. All right, so we're going to get with F anchor. Okay, I'm going to bring that one out front. Okay. All right, and so we get all these fancy numbers with nice newtons on here, and I'm very proud of how some of these minus signs worked. Well, they just look pretty, you know. Every now and then you look back at your handwriting and you're like, that was really nice. All right, anyway, so this is the pressure pushing downwards. This is the weight of the nozzle. This is the weight of the water. I think you can see already that these are negligible. We could have ignored these in this case. Okay, it's going to take some more time working with these before you start to get an intuition about what you can neglect. But you can see that those are so small they don't even matter. And then you can also see that really the water entering, so this is the momentum flux going in, this is very small, okay, compared to it leaving the system. Okay, so and that should be expected. Okay, I mean, if you look at this, okay, this stuff is leaving at over 3 times as fast. Okay, so because it's leaving at over 3 times as fast, over 9 times as fast. Okay, you can expect this term, especially because it's not on an angle, to be more than 9 times as big. Okay, and you can definitely see that. 2 to 18 would be 9 times as big, and this is more than that. Okay, so anyway, like I said, in this class, include all the terms because you don't have that intuition yet, but it's just something to be aware of. So notice that if we move this all around, the anchoring force ends up being positive, and it ends up being 77.7 newtons. Okay, upwards. Okay, exactly as we would expect. Okay, because if you were to all of a sudden unscrew it, it would fly downwards. Okay, because all the water would be pushing it downwards. Okay, so that is how you solve this one. Okay, and the nice thing about this problem is it's 1D. Okay, 1D problems are great. We don't have to do any X directions. We don't have to do any Y directions. The Z is all we need. Okay, give Z a chance. Z is all we need. Ooh. It'd be nice to meet you guys in person so you could see that I'm actually, I don't know, that I enjoy being a little ridiculous. I don't know if any of that is coming through. Anyway, before we do the next one, let's go ahead and grab these tools. Let's bring them down here. We'll go right over here, and I will write out the problem. All right, so here's our problem. I'm not sure we're going to use many of our tools here. This is a short problem, but it has one little tricky thing, and it gets out the thing that my students hate the most. Okay, so let's see. So we've got some barge here. Hey, my barge friend, you're floating along. And what's happening? Well, there's a dredger that's loading sand onto it. So I drew it in yellow, so it's probably pretty hard to see. But here's the sand pile, and it's kind of flopping out onto that thing. And sand, of course, is more dense than water. It's 2.5 times, or in this case, 2.65. Most rock, you will give it a dry specific gravity of 2.65 is pretty standard onto a barge. Sand behaves like a liquid and leaves the dredger at 5 feet per second and 800 pounds per second. Find the tension in the mooring line. So you can imagine in this case that if that mooring line were to cut, this barge would float off to the right. However, it is not floating off to the right, so that means that the mooring line is probably in tension and is probably pulling the barge to the left. Okay, so this is pretty challenging. So what I'm going to do, again, if this behaves like a liquid, then we've got a liquid and we're looking for a force. So we know we're going to use the momentum equation, and I want to do the free body diagram, and I want the free body diagram to include the thing that I'm solving for. Okay, so what I'm going to do is I'm going to draw a little dotted line like this, and this is going to be the thing that I'm going to draw a free body diagram of. Okay, so it's going to be it looks like I'm kind of drawing the barge and sand. Okay, so basically I've got this thing, and I'm not really going to do a great job of drawing it, but here it is, and there's one force going this way, which I'm going to call the tension. There's a buoyant force going this way. There's a weight going this way, and fortunately I'm not really too concerned about either of those, because I only want the tension, which means I'm only going to be working in the X direction. And then I've got, because I like to draw these in blue, okay, I've got I'll call this V. Okay, it doesn't have to be V1 or V2 because there's only one V. in this case. Okay, and that's coming in at 30 degrees. Okay, and that's a momentum flux coming into this problem. Okay, so what I'm going to do is I'm going to look up over here at my tools. Obviously, there's no manometer. There's almost no geometry to this problem. There's no continuity, really. And so let's do momentum. Let's just line it up and let's try momentum and see what happens. I knew that I was going to have to use it. So let's see. We only care about the x direction in this case. So let's see. So it's the sum of the forces in the x direction, okay, plus the sum of the momentum fluxes coming in, rho. Well, not a well, it could be a rho, but usually we do the way I've been doing it for you guys is v x rho q, noting that that x means that that's the only one that's going to get an x direction on it, equals the sum out of vx rho q. All right, let's see here. So the sum of the forces in the x direction, we've got a negative tension. We don't have any other forces in the x direction, do we? No, we have no other forces. Okay, we have a momentum flux coming in, though. Okay, so that's going to be v times cosine 30, because we need to make sure that let's just call that theta for now, equals theta, cosine theta. Okay, rho q equals, and we don't have anything leaving this system, so that's going to be 0. Okay, so in other words, tension equals v cosine theta rho q. Okay. Boom. Super easy, right? Maybe. Okay, let's see. What's v? 5 feet per second. Golden. Cosine theta. Theta's 30. Golden. Rho. The density of the sand is easy because we know it's 2.65. So it's going to be 2.65 times what? Think times what? What's the density of water in the English system? What is it? Oh, that's right. It's 1.94 slugs per cubic feet. All right. Well, what's Q? What is Q in this case? Okay, this is the problem here. Is we've got this thing right here, and this is really a painful thing to look at. Okay, pounds per second. Okay, so this is going to be awful. We don't have Q. Okay, so what I want to do is I want to kind of look at this thing, 800 pounds per second. Okay, so this is clearly a rate, right? So it could be a Q maybe, except for the fact that Q is volume per time. This is pounds per second. So it sounds like it's a force per second, except it's not a force per second, right? Because it's not applying this 800 pounds per second. This is one of the few times that, at least in my class, you will end up with something that is a pound mass. Okay, so this is a pounds mass per second. Okay, so what is that? Well, that is mass per time. So what is that? Well, mass per time is m dot, okay, or that is rho q if you wanted to. Okay, so that is this right here. Okay, so I know what you're thinking, and it's quite a thought, really, that thing that you're thinking. And maybe it will work even. So let's try that thing that you're thinking and see what happens. Okay, to see if it works. So you're thinking to take this, because it's rho q, plug it in right there, and solve this thing. And let's see what happens. T equals v, 5 feet per second, cosine 30 degrees. Okay, rho q, 800 pounds mass per second. Okay, now you're thinking this is golden, right? We're about to get an answer because you're just going to plug all this nonsense into your calculator and you're going to get a number. And you got a number of, it looks like you got 3,464.1. And then because if you're like most of my students, you didn't bother even writing any of this stuff down. So you just got here and you wrote, well, tensions in pounds, so I'm going to put pounds. Or you forgot what units you are and you put newtons. But let's focus on if you wrote down pounds. Okay, do you think a pound mass times a foot, okay, is a pound mass times feet divided by seconds squared equal to a pound? The answer is no. Okay, so you would get points off here. I don't know how many, because there's not really a lot going on in this problem. Probably if you got to this, that would probably be 8 of the 10 points, or I don't know, 6 of the 10 points. But plugging in the numbers matters here. Okay, and this does not work. Okay, so what we really need to do is we need to go back over here, and we've got a certain number of pounds. To get an m dot needs to be measured in slugs per second, okay, in order to be able to be plugged in. Okay, because this equation down here below, to make it work, to make this work right here, I need to, come on, punk, erase. Thank you, sir. Okay, I need this to be slugs. Okay, now you might say, well, how am I supposed to remember that? Well, you know that in the English system, the metric system, kilogram meter per second squared is a Newton. Okay, note this is exactly the same thing. Okay, mass times acceleration equals force. Okay, so we need this to be in slugs per second. Okay, so how do we get from pounds mass to slugs? Well, 32.2 pounds mass per slug. Yeah, that's right. Okay, so what we're going to do is we're going to take this 800 pounds mass per second. I'm going to multiply that by 32.2 pounds mass per one slug. All right, so this is our row Q right here. Okay, that we can plug in over here. Okay, so if I'm going to take my little fancy eraser tool, which never works, sure enough, it's not working now. Oh, it's kind of working. Hey, buddy, let's do it. Woo-hoo! Yeah. So then we're going to type it in, and we're going to get, oh, man, where's my calculator? Good for nothing, punk. 24.845 slugs per second. Okay, and then we're going to go and we're going to erase this incorrect answer because we don't like incorrect answers. We prefer correct answers. And again, this is a question of perseverance. And we are going to get 107.58, 107.58. And the tension equals 108. And let's see here, we've got feet, seconds squared. So that's an acceleration, and here's a mass. Mass times acceleration squared gives us pounds. Okay, so this is 108 pounds. Okay, and that's one of the many ways that we need to use units to make sure that we did not screw up our work. Okay, because this is very easy to mess up, right? Especially because we don't really use slugs very often. In fact, we have a lot of crazy professors who teach you pounds mass. These are crazy professors. Okay, we love them. They're doing the best they can, but they're crazy people. Okay. I don't know if you've noticed, but they're crazy. Okay, so anyway, I hope y'all having a good day. Take care of yourselves. I'm sending you laughs. I hope all is well. This material right here, this will be the last thing on test 2, at least for this semester. What semester is it right now? It is the COVID semester, so it's October 19th. Hopefully, October of 2020. Hopefully, this does not continue to be. We don't have, COVID semester after COVID semester after COVID semester. Or maybe the next one will be called the Wayno virus or something, because we're going to have some new kind of stupid virus. I hope no more viruses. Anyway, I hope y'all are doing well. Take care of yourselves. Know that I don't know you, but if I did, I would probably tell you that I love you. I don't not love you. I just don't know you. So y'all take it easy. Take care of yourselves. Take care of each other. Let me know if I can help you. All right, that's it. And be easy. And that's it. So give fluid mechanics a chance. All we are saying. Bye. I hate when it does that.